This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on Taylor and Maclaurin series. A Taylor series is a polynomial that's centered at 0. So what does that mean? A0 is our first coefficient plus A1 times x minus 0 plus A2 times x minus 0 squared plus A3 times x minus 0 cubed. This is centered at 0 because if you plug in an x of 0, all of these terms go away. Now obviously x minus 0 was just x, so we typically write it this way. So Maclaurin series is of the form a0 plus a1x plus a2x squared plus a3x cubed, etc. And then we can write it this way in terms of summation notation. The sum is k goes from 0 to infinity, a sub k x to the k. A sub 0 x to the 0, which is 1 of course, so a0, a sub 1 x to the 1 plus a sub 2 x to the 2, etc. So that's our general form of a Maclaurin series, and we use the term Maclaurin if it is centered at 0. So we want to construct a Maclaurin series for f of x equals e to the x. Let's go through the whole process. We're going to have to find a bunch of derivatives of f of x and see what their values are at 0. So f of x is e to the x, the first derivative is e to the x, second derivative is e to the x, third derivative is e to the x, fourth derivative is e to the x. And I want to evaluate all of those derivatives at 0. So f of 0 is e to the 0 is 1, f prime of 0 is e to the 0 is 1, etc. All of the values of the functions, the derivatives at 0, are always 1. That makes this a little easier for this to work with. Now our strategy is going to be to look at that Maclaurin series and solve for the coefficients by forcing the function f and the polynomial p to agree at 0 for all of its derivatives. So let me show you what I mean by that. So here's our polynomial p of x, a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the fourth. If I plug 0 in for x, gone, 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 all that's left is a sub 0. So p of 0 is a sub 0, f of 0 is 1, so a sub 0 is going to be 1. First derivative, a1 plus 2a2x plus 3a3x squared plus 4a3 x cubed plus dot, dot, dot. Plugging in 0, 0, 0, all that's left is a1, so p of 0 is a1. Check that should be p prime of 0. Let me go ahead and fix that. So p prime of 0 is a1, f prime of 0 is 1. So you can see that a1 is going to have to be 1 because we want the function's first derivatives, polynomial's first derivative, to agree at 0 at our center point. P double prime of x, 2a2 plus 6a3x plus 12a4x squared, etc. Plugging in 0 for x, all I'm left with is 2a2. Second derivative is here is 2a2, second derivative there is 1. 2a2 is 1, so a2 would have to be 1/2. Third derivative, same process. You can see we're going to have something x squared, something x cubed. But plugging in all those zeros, those all disappear, and p triple prime of 0 is just 6a3. And that's going to have to agree with f triple prime of 0. That's going to have to agree with 1. If 6a3 is 1, a3 will be 1/6. Then we finish that process. The fourth derivative, 24a4 plus something x squared plus something x cubed, etc. Plugging in 0, all that's left is 24a4. That's got to be 1. So a4 will be 1/24. So our goal is to find a Maclaurin series, again centered at 0, for f of x equals e to the x. We can go ahead and solve for a0, a1, a2, a3, a4, etc. And I talked about that on the previous page. Just one more time, a0 is 1. a1 is 1, 2a2 is 1, so a2 is 1/2. 6a3 is 1, so a3 is 1/6. 24a4 is 1, so a4 is 1/24. What you will recognize is 24 is 4 factorial, 4 times 3 times 2 times 1. 6 is 3 factorial, 3 times 2 times 1. 2 is 2 factorial, 2 times 1. 1 is 1 factorial, 1. And 1 is 0 factorial, in case you forgot. 0 factorial is 1. So I have the first 1, 2, 3, 4, 5 coefficients for our Maclaurin polynomial. So our p of x up to the fourth power is 1 plus 1x plus 1/2 x squared plus a 6x cubed plus a 24x to the fourth plus dot, dot, dot. But thinking of the factorials, it's relatively easy for us to write that in an alternate form. So this is where we are up to the fourth power, and then putting some dot, dot, dots to recognize that this goes forever. And again, 1 is 1 over 0 factorial, 1 is 1 over 1 factorial, 1/2 is 1 over 2 factorial, a 6th is 1 over 3 factorial, a 24th is 1 over 4 factorial. So our pattern is established. It's x to the k over k factorial, x to the 0, 1 over 0 factorial, plus x to the 1 over 1 factorial, plus x to the 2 over 2 factorial, etc. Once we're here, our next strategy is to find the interval of convergence. So what does that mean? For which values of x does this converge? We're going to use the ratio test. So I need the absolute value of a sub k plus 1 and the absolute value of a sub k. Take their quotient and look at the limit. So absolute value of a sub k I have here, absolute value of x to the k over k factorial, which we can write as absolute value of x to the k power over k factorial. K is always positive. No need to worry about absolute values there. How about a sub k plus 1? Replace the k with k plus 1, x to the k plus 1 over k plus 1 factorial. Absolute value x to the k plus 1 over k plus 1 factorial. With the ratio test, we take the limit of absolute a sub k plus 1 divided by absolute a sub k. If we get a limit that is less than 1, then we know it converges. If we get a limit of more than 1, it diverges. If we get a limit of exactly 1, the test is inconclusive. So let's take a look. Absolute a sub k plus 1 divided by absolute a sub k. This divided by this. So of course we're going to invert and multiply. So let's think about this. X to the k plus 1 over x to the k, the exponents differ by 1. So I get absolute value of x upstairs. K factorial over k plus 1 factorial. Think about like 6 factorial over 7 factorial. 6 factorial, 6, 5, 4, 3, 2, 1. 7 factorial, 7, 6, 5, 4, 3, 2, 1. All that's left is 7. Well, k factorial over k plus 1 just leaves me with a k plus 1 downstairs. We need to look at the limit of this as k goes to infinity. So the limit as k goes to infinity of absolute a sub k plus 1 over absolute a sub k is the limit as k goes to infinity of this, absolute x over k plus 1. K is changing, so I can bring the absolute value of x out in front of the limit operator. So I have absolute x times the limit as k goes to infinity of 1 over k plus 1. Now regardless of what x is, this limit is always 0. 0 times absolute x is always 0. And on the ratio test, if you get a limit that is less than 1, it converges. Our limit is 0, therefore this has to converge for all values of x. And we conclude that the interval of convergence is from negative infinity to infinity. So regardless of the value of x, this will converge. So this, in essence, is our definition of e to the x. E to the x is defined by that sum. Let's look at a Taylor series. Now we said a Maclaurin series was centered at 0. A Taylor series is centered anywhere, so at x equals c. So here is our general form, a0 plus a1 times x minus c plus a2 times x minus c squared plus a3 times x minus c cubed plus dot 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 to infinity. Which written this way, sum as k goes from 0 to infinity of a sub k, x minus c, where it's centered, to the k. And in a Maclaurin series, c was 0. General Taylor series, c can be anything. So here's our example. We want to take a look at f of x equals natural log x, and we want to center it at c equals 1. So you'll notice I replaced all of the c's with 1. And if I plug 1 in, you'll notice everything disappears except the leading term. So in this case, p of 1 would just be a0. But let's take a look at our f of x here. F of x is natural log x. F of 1 is natural log 1, which is 0. The derivative of log x is 1 over x, which I've written here as x to the negative 1 to make the derivatives a little easier. So f prime of 1 is 1 over 1, which is 1. Second derivative of x using the power rule, negative 1x to the negative 2, or negative 1 over x squared. Plugging in 1, negative 1 over 1 squared, we get f double prime of 1 is negative 1. For the third derivative, negative 2 times negative 1, positive 2x to the negative 3, which means 2 over x cubed. That, of course, should be f double prime of 1, so let me fix it. So f double prime of 1 is 2 over 1 cubed. 2 over 1 cubed is 2. Now for our fourth derivative, using the power rule, negative 3 times 2, negative 6x to the negative 4. which is negative 6, over x to the fourth power. The fourth derivative at 1 is negative 6 over 1 to the fourth, which is negative 6. Now let's remind ourselves of our goal. Our function was f of x. We want the function and the polynomial to agree at all of the derivatives at 1. That's our goal. So I will need to take the derivatives of p of x and look to see what's happening at 1 as well as we do that. So there is my p of x. P prime of x is what? The derivative of a naught is 0. That goes away. This, of course, is 1 times a1. The derivative of a2 x minus 1 squared is 2a2 times x minus 1. The derivative of x minus 1 is just 1. The derivative of this piece, 3a3 x minus 1 squared times 1, etc. So if I plug 1 in, gone, gone, gone. P prime of 1 is just a1, so keep that in mind. Second derivative of this piece is 2a2. 2 times 3a3, 6a3 times x minus 1 to the first times 1. And then this should be a 3 here, so let me go ahead and fix it. So the derivative of 4a4 x minus 1 cubed would be 12a4 x minus 1 squared. Plugging in 1, plugging in 1, plugging in 1, all I would be left with is 2a2. Continuing now with our third derivative, we get 6a3 plus 24x minus 1 to the first power plus something x minus 1 squared plus something x minus 1 cubed. Plugging in all these 1's just leaves me with 6a3 with my first term. And for the fourth derivative, 24a4 plus something x minus 1 plus something x minus 1 squared plus dot, dot, dot. But plugging in all the 1's, everything goes away except for 24a4. So p of 1, everything goes away, a naught. P prime of 1, everything goes away but a1. P double prime of 1, everything goes away but 2a2. P triple prime of 1, 6a3. P quadruple prime of 1, 24a4. So I want f of 1 and p of 1 to agree, f prime of 1 and p prime of 1 to agree, f double prime of 1 and p double prime of 1 to agree, f triple prime of 1 and p triple prime of 1 to agree, f quadruple prime of 1, p quadruple prime of 1 to agree to see the pattern. And our goal is to solve for all of those coefficients. So here's what we have. So a naught is 0, a1 is 1, 2a2 is negative 1, 6a3 is 2, 24a4 is negative 6. So of course a naught is 0, a1 is 1. If 2a2 is negative 1, then a2 is negative a half. If 6a3 is 2, then a3 is 2/6 or a third. If 24a4 is negative 6, then a4 is negative 6/24 or negative 1/4. So we have a 0, a1, a2, a3, a4. So we have a polynomial up to the fourth term, but it's pretty obvious what that is going to be in terms of our pattern. You'll notice it alternates plus, minus, plus, minus. The denominators here, the denominator is 1, then 2, then 3, then 4. So we have it in this form, and then we can rewrite it this way. You'll notice x minus 1 to the k over k, x minus 1 to the first over 1, x minus 1 to the second over 2, x minus 1 to the 3 over 3, with the fact that it starts out how? It starts out as a positive number, so negative 1 to the k plus 1 will handle that. Interval of convergence, we have this. A sub k plus 1 is that. A sub k is that. If I divide those guys, we get this. So, cutting to the chase a little bit here, k over k plus 1 times absolute k minus 1. I need that to be less than 1. When is that going to be less than 1? We're going to take our limit. So our limit of that is simply going to be absolute x minus 1 times the limit is k goes to infinity over k times k plus 1. That limit is just 1. I get absolute x minus 1. Which means that x has to be between 0 and 2, at which point you would have to check the endpoints. So I encourage you to go ahead and plug in those numbers and see what values you get for those endpoints. And that concludes this lesson.